Now we'll look at our first example from section 3.1 on functions. We are to determine whether the relation given is one of those special types of relations called a function. And if it is a function, we're to indicate the domain and range. So in part A, we have sort of a mapping situation, right? That's what this is. This is mapping. And our x values, or our independent variable, is level of education. And so we have no high school diploma, some college, and college graduate. And then we have unemployment rates as our outputs. 7.7% is matched up with no high school diploma, and so on. So would this represent, this is a relation between two variables, x and y, or whatever assignment we'd want to give to those variables, but it's a relation between the two. But is it a function? And we ask, is each x associated with exactly one y? Well, yes, it is. Of course. So each one is associated with exactly one y. So this is a function. There's not a lot of room here, but I'll write function. And it said, if it's a function, tell the domain and range. Well, let's just indicate that this list is our domain, and this list is our range. Okay, so this is a function because each one of these inputs only gives us one output. Now, would it be possible if we know high school diploma and high school diploma shared an unemployment rate? Sure, that could happen. They could have the same unemployment rate. But you couldn't have no high school diploma having two different unemployment rates. That wouldn't make any sense. Let's look at B. We have a set of ordered pairs. So this was mapping. These are ordered pairs. And the question is, this is a relation between x's and y's, but is it a function? So the question is each x associated with exactly one y? So 2 is matched with 3, and look, 2 is matched with -1. So this is not a function. Why? Because 2 corresponds to 3 and 2 corresponds to -1. You can't have that, right? So each x has to be paired with only one y. The output has to be, we can only have one output. When we put in 2, there's only one possible output for that, whatever it would be. But in this case, we have 2. So this is a relation, but it is not a function. So we don't need to state domain and range. Okay, here's another set of ordered pairs. Again, we're looking to see if each x is associated with exactly one y. So -2 goes with 3. Does -2 go with anything else? No. 4 goes with 1. 3 goes with -2, and 2 with -1. So this is a function because each x is associated with exactly one y. And our domain, I'll just use a capital D, is the set -2, 4, 3, and 2. And our range is the set 3, 1, -2, and -1. These are just lists. It doesn't matter if they're in a particular order. That's roster notation. Okay, so this one is a function because we don't see any, what are we noticing here? The repeated x. X was repeated here, so that gave us a clue that, wait a minute, for two different inputs, for the same input, sorry, we're getting two different outputs. But here we don't even have the same input repeated, so we know this is a function. That's the kind of the quick way to check. Did we repeat any x's? We did not. We have a function. Okay, so let's try that here. Did we repeat any x's? 2, 4, -1, 0. No, so we know we have a function. When we have ordered pairs, that's the quick way to do it. Notice that when you put in 2, you get 3. When you put in 4, you get 3. And -1 gives you 3, and 0 gives you 3. But the question is, does each x get associated with just one y? And it does. It doesn't say it has to be unique for that x. It just says that 2 only gets 3 and nothing else. And that's the case. So our domain is the set 2, 4, -1, 0. These are just all the x's, right? All the x values is the domain. And the range, I don't need to write it several times. It's just 3. Okay, this is a function. This is like that mapping, the picture we had previously, where two different x's went to the same y. In general, the idea behind a function is its predictability. In other words, if you put in 2, you have to get -1. You can't put in 2 and maybe get 3, or put in 2 and get -1. So this is not predictable. You don't know what the outcome is going to be if you put in 2. But here, you always know. You put in 2, you get -1. Here, if you put in 2, you get 3. Okay, so it's predictable. If the input is known, we can use the function to determine the output. With non-functions, we don't have this predictability. Okay, so if you know that somebody has some college, then you could predict that the expected unemployment rate for someone in that group would be 5.4%. It's predictable. Sometimes it's helpful to think of a function f as a machine that receives as input a number from the domain. That's your input, a number from the domain. It manipulates it and then outputs the value with certain restrictions. So it would only accept numbers from the domain of the function. And for each input, there is exactly one output. It's predictable, right? So for a function y equals f of x, maybe you've seen this function, it's what we call notation. Y is a function of x. These are interchangeable in an equation. We can take out the y, put in f of x. The variable x is called the independent variable. Because it can be assigned to any of the numbers in the domain. So x can be any of the numbers in the domain. The variable y is called the dependent variable. Because its value depends on x. So we plug in the x and we wait for the y to come out. So it's like a machine. For example, if we had our equation, remember we said we could use an equation like y equals 2x minus 1. So into our machine would go, say, the number x equals 0. It's predictable what's going to come out. Y equals -1, right? Input and our output. It's predictable.